Hi everyone, today we're going to look at Gauss-Legendre quadrature methods. I'm going to do a quick bit of theory and then I'm going to do two quick worked solutions. So what we're essentially wanting to do is we want to evaluate uh, uh, an equation from A through to B. This is an integral equation of f of x. And let's go dx. Close it off. We want to evaluate something like this, but either f of x has not got an explicit integral, or it's going to be extremely difficult to determine. First thing that we want to do with the Gauss-Legendre method is we are going to consider a number of nodes, and those nodes are going to be x1, x2, all the way up to xn. And we are going to consider a series of coefficients. So coefficients, and these are, we're going to call these C1, C2, all the way up to Cn. And these are going to be selected to minimize error. The first principle that we're going to be assuming within this is that when we take our integral from, let's go A through to B of f of x dx, we are going to be assuming that is approximately going to equal some function where I is equal to 1 through to n, and we are going to be stating we're looking at ci times f of xi. Make sure that's clear. Ci f of xi. We're assuming this. Now, if we took a limit of n towards infinity, then obviously this would be a nice, obvious and easy definition of an integral, but we are obviously, since we're approximating, not taking it to infinity. So that's the fundamental principle of it. The important things to note are your nodes over here. They're not necessarily going to be equally spaced, and in figuring everything out here, all the nodes and your coefficients, we can treat these coefficients like they're variables when we're solving, because at present we don't actually know what they are. So what that means is we can say that in order to solve what they are, we're going to need an equation. I'm going to need an equation with 2n parameters. And what I mean by that is we have got n parameters in terms of nodes. We've got n parameters in terms of coefficients. So we need something with 2n parameters because we need to solve for both. As such, we are going to want a polynomial at our a plus bx plus cx squared plus etc. We're going to want a polynomial of degree 2n minus 1 degree. We want something of that degree at least, because a polynomial of that degree will have at least 2n parameters. So what I'm talking about, just so that you understand here, we're going to do a quick derivation. Let's say that our n is equal to 2, so it's of degree 2. If we want to, we're going to be saying that we're going to have an integral of, let me put in an f of x, integral of f of x dx, and we're going to we're going to make our equation easier to understand, and this is one of the founding principles of the Legendre implementation. We're going to look from -1 through to 1. These are our boundaries, because if we are looking on either side of 0 just by a single unit, that will make our life much easier. What we have said above, if we have a look at this, our defining equation over here, we're going to write that out. We are going to be able to state that this, using our 2n parameters, is going to approximately equal C1 f of x1 plus C2 f of x2. This is our degree 2. Now, our second point that we need to do, well, we want to simplify this. Because simplifying f of x is, we can't directly solve this because we know that f of x is a difficult equation to solve, we can start to separate f of x. We have said that we need it to approximate it as a polynomial, so we can expand it in the form of a Taylor series. We'd be able to approximate it to be, let me just put this down, so we could approximate f of x as a Taylor series to be equal to a1, sorry, a0, that's going to be our initial term, plus a1x plus a2x squared plus a3x cubed. And here we have managed to expand it, and we can now start breaking it down. If we substitute this back into our earlier equation, we now are left with an equation that reads from -1 through to 1. And inside now we have a0 plus a1 x plus a2 x squared plus a3 x cubed dx. Or we could write this out in another way where we can go a0 integral -1. I'm going to leave these just in black because it's going to be quicker. a0 plus a1 integral -1 to 1 of x plus a2 integral -1 to 1 of x squared dx plus a3 integral -1 to 1 x cubed dx. And that is just breaking up according to our laws of calculus and how we can subdivide a polynomial in terms of calculus. Now, remember what we were saying where we were approximating it earlier. We were saying that we can approximate it as such, like this. So one of the key things within Legendre is this is only going to be exact when f of x is going to be equal to 1, x, x squared, or x cubed. Then we're going to have an exact solution. So what we can then state because of that, let me just get it to move down, is we can start subdividing these up. We can go c1 of 1, if we're looking at just this term over here, c1 of 1 plus c2 of 1 is equal to integral -1 to 1 of 1 dx. And then we can go c2 of x, and I'm going to call this x1 because remember, according to our polynomial above, we are looking at c1. This is going to be x1 and x2. Our function is what is contained within the integral. So here we have c2 f of x. Our f of x is just x in this case, plus c1 over here. c1 x1, c2 x2 is going to be equal to integral -1 to 1 of x dx. And so we can continue this up to x1 squared for each of these options that we have. Squared, and we land up with -1 to 1 x squared dx. And our final one, if we're going to look at the x cubed over here, we can then write that one out. c1 x1 cubed plus c2 x2 cubed equals integral -1 to 1 x cubed dx. Now, if we have a look at our individual integrals now, because it's a Taylor series, we can very easily integrate each of these. And we know that this is going to be equal to 2. This is going to be equal to 0 because we've got an odd value in the exponent. This one we know is going to be equal to 2 over 3. And this one is going to be equal to 0, again, odd exponent. And what we have here is equation 1, 2, 3, and 4. And we've got 4 unknowns, c1, c2, x1, and x2. It becomes a process of simultaneous equations, or you can use a matrix method if you wish. but you should land up solving this with c1 is equal to 1, c2 is equal to 1, x1 is equal to minus 1 over root 3, and x2 is equal to 1 over root 3. And these are very fixed solutions in terms of this equation. What we can then approximate is, if we have our minus 1 to 1 of f of x dx, we can say it is going to be approximately equal to c1, which is 1, times f of x1, which is going to be 1 over minus root 3, plus c2 times f of x2, 1 over root 3. And what's important to note, here I'm looking at the approximation of just f of when n is 1, but we could increase our n as needed. What we end up coming up with here is an approximation for our f of x, and we could, if we wanted to, if we made this element squared and squared, then we'd be approximating for f of x is equal to x squared, and so forth. What we can do from here is then just solve this, and this will give us our approximation from minus 1 to 1. That's the theory. I'm now going to do some quick work questions. The work questions should help clarify just the understanding of everything a bit better, so I hope that does help.